Hi, welcome back after the weekend. I believe we're on day 22, and today's episode is brought to you by a small K. And you'll see it's going to figure pretty prominently in just a little bit. I hope you've been working hard on your review sheets the last couple days. Don't forget, tomorrow you're going to see your test on work and energy. Right now though, we're going to talk a little bit about electric forces and Coulomb's law. Like up to now, what do you know about electric forces? Well, you know that like charges attract. Oh, I screwed that up. Like charges repel and opposite charges attract. Yeah, that's the way it goes. But just how big is that force of attraction? How big is that force of repulsion? That's where Coulomb's law comes in. It allows us to calculate exactly how big those forces of attraction or repulsion are. First of all, let's do a little bit of review with regards to units. You'll remember that one elementary charge is a charge on a proton. And of course, positive one elementary charge would be the charge on a proton. Negative one elementary charge, well, that's going to be the charge on an electron. And if you take a whole bunch of elementary charges and clump them all together, for example, or to be more exact, 6.24 times 10 to the 18th elementary charges, that's a lot of elementary charges, right? If you take that many elementary charges and stick them all in one place, well, you've got a charge equal to 1 Coulomb. Also, here's a number that you're probably going to be using quite a bit. Remember that an elementary charge is just a little tiny fraction of a Coulomb. And if you do the arithmetic, and I'm pretty sure you can figure this out on your own, it's one of the calculations we did last year. One elementary charge is equal to 1.6 times 10 to the minus 19 coulombs. Very nice number to have committed to memory. Anyway, let's talk about Coulomb's law. So suppose we have two charges, Q1 and Q2, and for whatever reason, I don't know why physicists like to use the letter Q to denote charge. Suppose these charges are separated by some distance r, and it looks like in this case, both these charges are positive or both these charges are negative because they are repelling each other. Okay, you can see that charge 2 exerts a force F on charge 1, and charge 1, it exerts the same force but opposite in direction on charge 2. Very nice of these charges. They follow just like everything else in this universe. Newton's third law: for every action force, there is an equal and opposite reaction force. Okay. Now exactly just how big are these forces? Well, that's where Coulomb's law comes in. To calculate just how big these forces are, there's how you do it. Okay. The force of attraction or repulsion between these things, F is equal to K times Q1 times Q2 over R squared. Looks familiar, right? That's basically the law of universal gravitation with a few letters changed around. Okay. Now, how about this K thing here? That K thing there, that is called Coulomb's constant. And if you look it up in a book, you'll find that K is equal to 9 times 10 to the 9th Newton meters squared per Coulomb squared. Okay. And how you arrive at units like that for K, well, you can probably remember it's going to be done the same way that you find the units of G in the law of universal gravitation. You basically solve this equation for K, substitute in the units. Okay. We won't bother with it. I'm pretty sure you can do that. But regardless, there are the units of K right there. Now, the significance of these units for you, of course, is that if you want your force to come out in newtons and you want to use this value of K, well, your distance is going to have to be measured in meters and your charges are going to have to be measured in coulombs. Now remember, sometimes you don't measure your charge in coulombs. Sometimes it's more convenient to measure your charges in elementary charges. In that case, you're going to have to use a different value of K. And if you're going to measure your charge in elementary charges, there is the K value, 2.3 times 10 to the minus 28. And you can see the units here are Newton meters squared per elementary charge squared. And again, the significance of these units, if you want your force to come out in newtons, if you want to measure your distance in meters, and you're using elementary charges for your unit of charge, well, then you use this value of K. All right, we're going to take another couple looks at some of the things, some of the little vagaries of Coulomb's law here, and then we'll do an example problem. Now remember, today's stuff is for the new unit, which is all about electric and magnetic fields. Of course, you won't see any of this stuff on your test. Now remember, we are taking a look at Coulomb's law, F equals K Q1 Q2 over R squared. And we're talking about K, and you should realize that K depends on units. And you know that already. You know that if you're using the big units of charge, coulombs, K is equal to the big number, 9 times 10 to the 9th. If you're using the small units of charge, elementary charges, K is equal to the small number, 2.3 times 10 to the minus 28. You should also realize that K depends on the materials surrounding the charges. Okay? We're using the values for K if the charges are in a vacuum. And to tell you the truth, if the charges are in air or pretty much any gas, as far as Coulomb's law is concerned, that's pretty close to a vacuum, and you can still use 9 times 10 to the 9th or 2.3 times 10 to the minus 28. But if your charges are in something like glass or plastic or rubber or copper, then you have to use quite a different value of K. We're not going to worry about that. As far as we're concerned, our charges are always going to be in a vacuum or something that behaves just like a vacuum as far as charges are concerned, like air. All right, something we should also mention about Coulomb's law. It is good for point charges only. Okay. Now if you take a look in this situation, Q1 and Q2, right now these things, they are point charges. Okay. But if I don't move these things apart at all, but I make them bigger, well, now they're not point charges anymore. For charges to be considered, for charges to be considered point charges, the distance across the charge must be insignificant compared to the distance between the charges. For example, if Q1 were down here and Q2 were way the heck up there, still the same size, well, now these things, they are considered point charges because, or at least you're pretty darn close to point charges because the distance across the charges is insignificant compared to the distance between the charges. And again, something you won't have to worry about a whole lot. Whenever we're talking about Coulomb's law, our charges, they always will be point charges. If they're not point charges, well, that's a good calculus question where you're going to have to integrate something for course later on. We'll be right back, and we will be taking a look at an example. We've got the whiteboards going in stereo here, and the use of another very high-tech physics implement. And we're going to take a look at the example in red. It says, find the total force on the proton below. And what we have here is a proton, and 10 nanometers from that, we have an electron, and another 5 nanometers further down the road, we have a couple protons clumped together. And where this situation might arise would be inside a particle accelerator, where physicists are smashing alpha particles into hydrogen atoms. If you take a close look at what we have here, we have a proton and an electron right beside each other. Well, essentially, that's a hydrogen atom. It's a proton with an electron flinging itself around. Over here we have two protons clumped together. That's basically a helium nucleus, which is, of course, an alpha particle, what a lot of radioactive substances give off. So at this instant in time, probably in some particle accelerator somewhere, we have a proton and an electron 10 nanometers apart, and in very close proximity we have a helium nucleus. And of course what we want to find out is the total force on the proton. And I'm pretty sure you will agree with me that the total force on the proton is going to be equal to the force that the electron exerts on the proton plus the force that the helium nucleus exerts on the proton. And essentially that's what I have right here. The force at A is going to be equal to the force at A due to B plus the force at A due to C. Okay. Get used to that notation. You're probably going to be seeing it quite a bit. The force at A is equal to the force at A due to B plus the force at A due to C. Now let's calculate the force at A due to B, the force on the proton due to the electron. So of course you've got two charges there, so you're going to be using Coulomb's law. And here it is. The force at A due to B is going to be equal to K times the charge at A times the charge of B over the distance between A and B all squared. Okay. All right, let's substitute in. Now, you got to remember that A is a proton and B is an electron. So it's probably way, way easier to measure our charges in elementary charges instead of Coulombs. All right, we're going to be measuring our charges in elementary charges, not Coulombs. I am using the small unit of charge. That means I want to use the small value for K. There it is. 2.3 times 10 to the minus 28. That's my K value. The charge at A is a proton, which is one elementary charge. The charge at B, also one elementary charge, because it's an electron. Now some people might say, well, shouldn't the charge at B be -1? Because let's face it, that's what the charge on an electron is, -1 elementary charge. Okay, true enough, and if you like, you can substitute in the value of -1 for QB, and then you can also use the fact whether your answer is positive or negative to tell you whether the force is attractive or repulsive. Entirely possible. But what I like to do is whether QB is positive or negative, it's not going to affect the value of the answer in the sense of how big it is. It's just going to affect the direction of the answer, whether the force is attractive or repulsive. So what I like to do is just substitute in the absolute values of the charges, okay, and I'll worry about the direction later, okay? So QA, positive 1 elementary charge, QB, the absolute value of that, also positive 1 elementary charge. The distance between the two charges, well, that's 10 nanometers. Remember, a nanometer is very small. A nanometer starts with a letter N. Well, -9 also starts with a letter N. So there is 10 nanometers right there. 10 times 10 to the -9. Okay, 10 nanometers. 10 times 10 to the -9. Don't forget to square it. And you grind that through your calculator, and what we come up with, you know what? You can probably do this without a calculator. Look at this. 10 squared is 100. 2.3 divided by 100 is 0.023. Now let's do the powers of 10. -9 squared, that's going to be 2 times -9, -18, -28. Take away because we're dividing. -18 is -28 plus 10, so that's, -28 plus 18, so that's 10 to the -10. Okay, make this one bigger by 2, so we got to make this one smaller by 2, and there's your answer. 2 times 10 to the -12. Don't forget, we're talking about a force, so it's going to be newtons. Now got a vector sign there, we need the direction of this force. Okay, remember, it's the force on A due to B, the force on the proton caused by the electron. Well, what is this electron doing to this proton? Well, it's going to be attracting it. Okay, so basically the electron is pulling the proton towards it in that direction. So the direction of this force is to the left, like so. And we will be right back to figure out the force on A due to C. I bet you can hardly wait for that one. All right, so we just figured out that the force on A due to B, there it is, 2.3 times 10 to the -12 newtons in that direction. Now we got to figure out the force on A due to C. So easy enough, right? The force on A due to C, you got two charges, so you're going to use Coulomb's law. That's going to be equal to K times one charge times the other charge divided by the distance between them, all squared. And this is easy enough to do. You could do it exactly like you did this one. You substitute in 1 elementary charge for QA. You substitute in 2 elementary charges for QC, because let's face it, that's 2 protons. And then for the distance, you substitute in 15 nanometers. That's going to be 15 times 10 to the 9th meters. Don't forget to square it. And you get your answer. Here's a bit of a shortcut though, which involves less number crunching, maybe less chance for error when you're using your calculator. And you'll see this done quite a bit in the solution, so I'm going to show it to you. Remember that when I substitute in these numbers, I'm basically going to be substituting in the exact same numbers that I used when I did this calculation. K is going to be the same, QA is going to be the same. This number though, look, it's going to be twice as big as the last time. This number is going to be twice as big as when I do this calculation. So basically, I'm taking this one and I'm increasing it by a factor of 2. And you probably know what's coming next. If this one goes up by a factor of 2, this one goes up by a factor of 2. How about this number? Well, instead of substituting in like I did the last time, 10 nanometers, I'm substituting in 15 nanometers. Basically, I'm taking the number down here and I am increasing it by a factor of 1.5, right? 15 nanometers is 1.5 times bigger than 10 nanometers. So I'm taking this number and I'm increasing it by a factor of 1.5. Now it's on the bottom and it's squared. So if this one goes up by a factor of 1.5, this one is going down by a factor of 1.5 squared. So my new force is going to equal to my old force, 2.3 times 10 to the minus 12 multiplied by 2 divided by 1.5 squared. And you do this on your calculator and you're going to get, I believe it's 2.04 times 10 to the negative 12 newtons. So I'll just go to one decimal place, 2.0 times 10 to the minus 12 newtons. Okay, now what's the direction of this force? The force on A due to C. So these two protons, what are they doing to this proton here? Well, this is positive, so these things over here, they're taking this proton and they are repelling it that way. So there is the force on A due to C. 2.3 times 10 to the negative 12 newtons in that direction. We'll come back and we'll figure out the final answer once and for all. We are just about ready to nail down the answer to this example. Remember, the total force on A is due to the force on A due to B plus the force on A due to C. And we figured out the force on A due to B, it's going in that direction. We figured out the force on A due to C, it's in the opposite direction. So when we add these two things together, well, let's just call this one here negative and add it. 2.3 times 10 to the minus 12 minus 2 times 10 to the minus 12. You can do this on your calculator. Can you do it in your head? Okay, think about it for a second. It's actually pretty easy to do in your head. I'm pretty sure everyone will agree that 2.3x minus 2.0x is equal to 0.3x. You know, 2.3 times something minus 2 times something is equal to 0.3 times something. Well, that's what we have here, except the somethings look a little weird. 2.3 times something minus 2 times something is going to be 0.3 times the something. And then change it to proper scientific notation. Let's make this one bigger by 1. So we're going to make this one smaller by 1. And there's your answer. 3 times 10 to the negative 13 newtons. This answer is positive. And the fact that it's positive means it is in the same direction as that one. The fact that it's positive, that implies that it is to the right. All finished. Okay, I will post an assignment that goes along with this. And let's see, tomorrow you're writing your test. That is on Wednesday. So, you know, don't worry about having this assignment done for tomorrow. You should have this assignment done for Thursday, however. And of course, keep checking back day to day for posts on whatever. Bye for now.